Hi, good evening. This is Umarish, your mathematics mentor. Welcome to Cumin classes. Before proceeding, let me make a request. Please subscribe the channel and hit that bell icon to receive timely videos. So without further ado, let's start the class. So first of all, let's do example 2. Before doing example 2, let's recapitulate and try to get some points, okay? Euclid's division lemma. We know that what's Euclid's division lemma? It's if a and b are two positive integers, there exists two positive integers such that a and b, two positive integers r and q, such that a equals bq plus r. Okay, where r should be always greater or equivalent to 0 and will be always less than this b. Okay. Okay. So Euclid's division lemma is saying us that you can represent any integer in the form of bq plus r. Okay, or you can represent any integer in the multiples of other integer. Okay, such that this r should be less or equivalent to 0, greater or equivalent to 0, and less than b. Are you getting? Okay. Now, suppose you have 4q. Can you represent any integer in the form of 4q plus r? Yeah, you can represent any integer in the form of 4q plus r, because that's what Euclid's division lemma is saying. Okay, r should be greater or equivalent to 0 and should be always less than this 4. What are the necessary equations you require to show any positive integers? What are they? They are 4q plus 0, 4q plus 1, 4q plus 2, 4q plus 3. Okay, these are all the necessary equations we require to show any positive integer. Okay, 3q plus r. 3. What are the equations you require? 3q plus 0, 3q plus 1, 3q plus 2. These are the only necessary equations you require to show, to represent any positive integer. But now there is a catch. If he is asking for even or odd, then there's the important point you must note. What's that important point? Let's come to that. Suppose we have, let's try to understand with the previous example, 4q plus 0, 4q plus 1, 4q plus 2, 4q plus 3. This is its generalized equation is 4q plus r. Okay. Now, since you know that if this will be even, okay, if this thing will be even, you are going to be sure whether the result will be even or odd. Okay. But if this thing will be odd, as in case of 3q plus 0, if this thing is odd, you are not going to be sure what are the results going to be. Let's understand. Okay. Suppose you know that even multiplied by even is always even. Okay. Even multiplied by odd is also even. Okay. So if here the number is even, it doesn't matter whether this is odd or even, it will always produce even results. Okay. Even. Okay. But if here the number is odd, okay, you get into ambiguity. Okay. You see, odd, let's try to reverse this equation. Odd multiplied by even is even. Okay. If this thing is odd, okay, if this thing is odd, you are going to get different results. Okay. For odd, you're going to get odd. For even, you are going to get even. So if the number here is odd, you are not going to be sure what the results will be. Okay, in the questions, if he is asking about even or odd, okay, if he is asking about even or odd, then it's necessary here that this number should be even. Okay, because this will be even, this whole will be even plus odd will be even, even plus even will be odd. Okay, sorry, even plus even will be even, even plus odd will be odd, even plus odd will be odd. You got it? Okay, now let's come to the question. Now let's come to the question. The question says, show that every positive in integer is of the form 2q and that every positive odd integer is of the form 2q plus 1, where q is some integer. Okay, can you write any positive integer in the form of 2q plus r? Okay, r should be greater or equivalent to 0 and less than b. Is that is that what's happening here? 2q plus 1, 2q. R is less than, greater or equivalent to 0 and less than b. That's what here is, that's what is happening here. Okay. Okay, what are the equations? 2q plus 0, 2q plus 1. Okay, is this even? Okay, so this whole term will be even because even multiplied by any integer gives us even results. Okay, is this odd? Because even plus odd is odd. Okay, so to represent any positive integer, sorry, to represent any positive even integer, we require just 2q to represent it. Okay, and to represent any odd integer, we require 2 plus 1, this form, to represent any positive odd integer. Okay, but you need to write this in exams. Let's see how you can write this in exams. Okay, you write first of all by Euclid's division lemma, we know that any positive integer can be represented in the form of 2q plus r, where r is greater or equivalent to 0 and less than b. Is that 2q, 2q and 2q plus 1. These are the two necessary equations you require to represent any positive integer. Since even multiplied by integer, positive integer will produce even results. Therefore, 2q can represent any positive even integer. And since even plus odd gives odd results, therefore 2q plus 1 can represent any positive odd integer. Is that clear? Now let's do example 3. This example is similar to example 2. Okay, what we need to show that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. Okay, can you write any positive integer in the form of 4q plus r by Euclid's division lemma? Okay, you can represent where r should be greater or equivalent to 0 and less than 4. What are the necessary equations? Since this thing is even, okay, you can know the results, whether the result is going to be odd or even. Okay, if this would have been odd, you would not have been able to find whether the result would have been even or odd. Okay, let's understand. 4q plus 0, 4q plus 1, 4q plus 2, 4q plus 3. Out of these, this is even. Okay, this whole term is even. Even plus 0 will be even, and this will be odd. This will be even, and this will be odd. Okay, you require these two equations to show any positive odd integer. Okay, hence proved. That is what question was asking. Okay, you are going to write this question by yourselves. Okay, let's move to other question. Now let's come to example 4. What does this example say? Okay, this is a simple example. This is a simple question of HCF. Okay, you have to find HCF using Euclid's division algorithm. Okay, what does this question say? A sweet seller has 420 kaju barfis. Okay, 420 kaju barfis. Kaju barfis, K barfis. And he has 130 badam barfis, 130 B barfis. She wants, okay, sorry, she is a woman. She wants to stake them up in such a way that each stake has same number. Okay, there's a condition that she wants to make stakes out of these barfis. Okay, condition is that each stake should contain equal number of barfis. Okay, each stake should contain equal number of barfis. Okay, badam, this is K. You will be having many kaju barfi steaks and many badam barfi steaks. Okay, we have to assume this stuff that you are not mixing them. You are staking them up separately. Okay. Okay. That each stake has same number. Okay, and they take up the least area of the trie. The next condition is that they should take least area of the trie. How is that going to be? They are going to take least area if you are going to stake as many barfis as you can. Okay, but the other condition that restricts it is that the barfis in each stake should be equal. So simply you have to find HCF of these two numbers. What's HCF? Let's find it out. 420 divided by 130. Okay, ones are, twos are, threes are. Let's do it with 3. 3 zeros are 0, 3 threes are 9, 3 ones are 3, 0, 12 minus 9 is 3. Okay, 30. How can you represent? 420 equals 130 multiplied by 3 plus 30. In the next step, you are going to take remainder as divisor and divisor as dividend. Dividend 130. 4s are 120, 10, and 130 equals 30 multiplied by 4 plus 10. Okay, then here 30, 30, 3s are 30. So 30 equals 10 multiplied by 3 plus 0. This 10 is HCF of, so this 10 is going to be HCF of 420 and 130. So you are going to stake them up in the pieces of 10. Okay, you're going to stake 10 pieces, okay, in each stake. Is that okay? Let's move to other examples. So let's come to exercise 1.1. Okay, 1.1. These are the first three questions. Okay, I've already taught you how to use Euclid's division algorithm to find the HCF of two numbers. You are going to do these questions by yourselves. Okay, I'll show just this part. Okay, one. Okay, question number one: how you have to use the Euclid's division algorithm to find HCF of these two numbers. Okay, how are you going to do that? You'll place 225 here, 135 here. Okay, one's a 135, 0, 12 out of 3, you'll get 90 here. You're going to take 225 equals 135 multiplied by 1 plus 90. Okay, 135, you're going to divide it again by 1. 90, 90, you'll get 5, 13 out of 9, get 45. Okay, represent this. 135 is equivalent to 90 multiplied by 1 plus 45. Okay, third step. 135, sorry, 90. 2s are 90, and this is the end of the HCF. Okay, you're going to get, how are you going to represent the last step? 90 equals 45 multiplied by 2 plus 0. You're done. You got the HCF. 45 is HCF of 135 and 225. Now let's do question second. What does the question say? Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. We know that by Euclid's division lemma that any positive integer can be represented in the form of 6q plus r. Okay, r should be lesser, greater or equivalent to 0 and always less than 6. These are necessary equations. 6q plus 0, 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4, 6q plus 5. Okay, out of these, you know, this is even. Okay, it will produce even results, and this and this will be even. Okay, out of only these three will be producing odd results. Okay, odd results, and these are all the necessary equation to represent all the odd integers. Okay, all the odd integers. Okay, that's what it was saying. Okay, you had to prove this and you proved it. Okay, let's come to question 3. An army contingent of 616 members is to march behind an army band of 32 members in a parade. Okay, 616, we have two groups, 616 and 32 members. Okay, you are going to divide them in such a way that they should make equal number of columns. You should make as many as columns out of 616 as you can make out of 32. So simply you have to do HCF. Okay, HCF, how to do? 616 divided by 32, ones are 32, it will be 9, 29, 6. Let's do it with 9. 9 2s are 18, 1, 9 3s are 27, 9 3s are 27, 29. Okay, you'll get 8 here. Divided by 32. 4s are 32. Okay, you got 8 as HCF. Okay, so you have to arrange these 616 members in 8 columns. 1 2 3 4 5 6 7 8, and these 32 in 8 columns. 1 2 3 4 5 6 7 8. Okay, okay, I think they are going to represent these 616 people. They'll be leading them in the form of 4 4. Okay, 8 columns. That's why he wanted to make us 8 columns out of both these numbers. Okay, was that clear? Let's proceed. Okay, now let's come to question number 4. Okay, use Euclid's division lemma to show that square of any positive integer is either of the form 3m or 3m plus 1. Okay, let us suppose that any integer can be represented in the form of 3q plus r. What are the equations? 3q plus 0, 3q plus 1, 3q plus 2. Okay, let's square this and find whether its square can also be represented in the form of 3q plus 3q or 3q plus 1. Sorry, 3m or 3m plus 1. Let's find it out. Okay, 3q, squaring both sides. Okay, x is equal to 3q. X square equals 3q square equals 9q square. Can this be represented 3 into 3q square? Okay, can you represent this term as m? So its square can also be represented as 3m. Okay, is this what we had to prove? Okay, let's go for 3q plus 1. Okay, let x be 3q plus 1. X square is equal to 3q square, 9q square plus 1 square plus 6q. Okay, this can be represented as let's get q terms together. 9q square plus 6q plus 1. Okay, let's take 3 common. 3, here will be 3q square plus 2q plus 1. Can this be replaced by m? So 3m plus 1. So that is what we needed to prove. Okay, lastly, let's come to this question, question number 5. It's similar to question number 4, but here instead of squares you have to prove cubes can be represented in these forms. Okay, I won't be doing this question here. I'll keep this question on you. Okay, you try to solve this question. If you are not able to solve this question, drop in the comments and I will show in the next lecture. Okay, what are the tools you require? You require a formula, that is a plus b cube whole cube equals a cube plus b cube plus 3ab a plus b. This is what you need for this to be proven. Okay, that was all for today. Before leaving, I would like to request, please subscribe the channel and hit that bell icon to get the videos on time, and share this video with your friends and classmates so that they can benefit too. So till next time, stay safe.